right, welcome back. Okay, so I will be continuing with the theme that Martin introduced, which is talking about the Karoo. So I won't get ahead of myself. So again, the implication is a more complex emplacement mechanism than just a single pulse. Also to explain sills on the sort of order of a couple hundred meters thick, but much less interesting than the Welsh ones we've been hearing about in terms of textures. So this is the Karoo supergroup in South Africa. So Martin was looking further to the northeast. And where we're going to be looking, this is the sedimentary basin part. All the little purple squiggles in there are doleritic sills. And then there are the volcanic eruptions, which are mainly exposed in or preserved in Lesotho, which is the circled little insert country there, the Drakensberg. So the stratigraphy of the Karoo is illustrated here. So it's topped off by close to 2 kilometers of basaltic lavas. And so that's the sort of final gasp of the Karoo is the magmatic event, which is also associated with the dolerites are associated with that as well. I'm going to get a crick in my neck if I try to do that. Okay, and the model is a plume model, as Martin alluded to. So there's some fins explaining the plume concept for as it applies to the Karoo. So in this part of the Karoo, in the sort of central part of South Africa there's a kind of special feature in terms of their emplacement. So the sills occur as these nested so-called saucer-shaped sills, where they turn up at the edges and then carry on again outwards. And there's been one quite detailed study done by a French and Norwegian group about 10 to 15 years ago. And they looked at a set of sills, the Golden Valley sill being the main one. And I've done the kind of cross-section there so you can see what the concept is. So this provides us with convenient exposures where in places where the road has been put through. So anyway, so Galern's detailed study, they deduced then that there are different geochemical profiles for different parts of the sill. And it's the part we are going to be mainly looking at is this inclined melt pathway section, because from an erosional point of view, the horizontal parts of the sill tend to either be under your feet on the topography or on the tops of these copies. So neither of them are that accessible for sampling, let's say. Whereas in the inclined paths, we can see along the road and get kind of sections straight through them. So so we see all the different elements preserved in different places. So on the top left, we see the tops of copies where the dolerites are preserved. And again, in the Beaufort group, which is kind of in the middle of the Karoo sedimentary basin pile, they tend to be on the order of a couple hundred meters. If you go deeper in the Karoo, they get thicker. So the thickest known ones are kind of near the base of that unit and into the Eka, hosted by deep marine sediments. And then they can get up to several hundred meters. And the thickest one, the one that actually has olivine cumulus and it has some copper mineralization, is nearly 1 kilometer thick. We won't be looking at that. So where we get these inclined sills, we can see them. There's a nice one just north of Colesberg, shown in the top right. We hardly ever see both contacts exposed. We often can get one very nicely shown, and then the other one is kind of the exposure has dissipated in that direction and it's not exposed. And we do get some very narrow ones. suggesting that this kind of morphological feature, which is apparently controlled by the amount of load on top. So the reason the stress field allows for that saucer shape, it's relatively rare. There's something like a half a dozen of these. There's some in the North Sea that have been well mapped out with geophysics. But they're relatively rare. So they don't occur higher or lower in the Karoo sequence in South Africa either. So yeah, here's a particularly nicely exposed one in a railway cutting where we see both sides of it well exposed. So where we sampled it then was in this area here in central South Africa. And so we've sampled 4 of these. And we just basically drove all over this area looking for places where we could see one very good contact and ideally have a good idea where the other one was. And then the Golden Valley sill that the Galern and colleagues studied is just to the southeast. Okay, so we can identify in the field the chilled positions of the chilled margins. As we've been talking about over the last day or so, the chilled margins in these are also kind of on the scale of a few tens of centimeters. And it's fairly obvious in the field where the chilled margin starts. Where it ends is less clear, but we can see it in the thin sections. So we sampled fair detail along those contacts. What we see are clumps of plagioclase are not uncommon in these, and these have been reported widely through the Karoo. But plagioclase phenocrysts, and in both clino and orthopyroxene phenocrysts, sometimes the enstatites are quite serpentinized, but they're nice euhedra. What we don't see are olivine phenocrysts in any of these chilled margins. So we can look at the bulk composition of the chilled margins. We can compare them to data collected from the basalts and from chills associated with the basalts from older work and from average compositions of our sills. So assuming they're kind of closed systems, and they all plot in a nice little clump reasonably consistently. And if we compare them to the literature, yeah, the literature data show a little bit of a shift upwards in this diagram, but I've interpreted that as an outcome of the fact that they've plotted all their iron as Fe2+. So they didn't make any kind of correction, whereas I have. So that would shift mine slightly lower iron. So if we look at the profiles across these sills, so now because we're looking at these inclined sheets, when we sample along them horizontally, we are effectively looking at a vertical section without having to use ropes to get to it. So what we see here are kind of uninspiring in terms of profile. So I'm interpreting these as immature S-shaped profiles. There doesn't seem to be any correlation with the thickness of the sill. So we don't see sort of more differentiation in the thicker sills per se. Arguably the very thinnest one shows the least going on, which, okay, that's fine. Makes sense. So interpreting this, the default interpretation or the default premise that previous workers on this was making was the kind of mobility of olivine as a cumulate phase within the vertical section to explain MgO variations. Now is olivine in a couple of these sills, but not in all of them. So there's quite a lot of pyroxene, there's quite a lot of orthopyroxene in the interiors, and it can be coarse grained. Olivine is not that common, and it's never coarse grained in these rocks. It's always these little clumps of fine grains gathered together with no inclusions of any other mineral in them. There's no evidence, bless you. There's no evidence of reaction with their surroundings. And they're not really much evidence that they've been resorbed. So it's not that clear whether this is compelling evidence that they could have crystallized and settled. So we'll come back to what the textures mean. So these are all quartz normative compositions, all of them. is there a way that we can have rocks start without olivine in them and then get olivine to show up? So, of course, on the assumption that they're all quartz normative, I assumed the answer was no, but they're just in that compositional space here where some of these at least are consistent with crystallizing plagioclase first, and then as they move away from the anorthite corner, they would then crystallize olivine second, in theory, for some of those bulk compositions. Most of them, it should be impossible. They should then go straight to plag OPX next. But there's no way to get, if we've got plag, orthopyroxene, and clonopyroxene appearing as phenocrysts, there's no way to get from that composition, which would be where the little red arrows are there, back to olivine, right? Not by normal fractional crystallization, not by doing something to it. So what are the possible explanations? So our magma does eventually crystallize olivine, and then some of it settles. We don't really see compelling textural evidence to support that. And we're not seeing very well-developed DNS-shaped profiles anyway that really require that. There's a very interesting model proposed by Galern et al. And colleagues, which I'm going to go through briefly just now, where movement of interstitial liquids creates a residue in the center that's Mg rich, which then crystallizes higher proportion of olivine. I have problems with this model, which is what I want to run by you guys. So the premise is that we're crystallizing from the outside in, so it's getting more and more, it's most solid at the edges and most mushy in the middle. So we can ignore most of the rest of this. So we have our initial liquid, hot in the middle, cold at the edges. Our solidification front is moving in, and as it's crystallizing, there is a density change that they are calling upon. So I think in their paper, they don't specify it, but you can look at the densities of basaltic liquids and basaltic rocks at the same temperature, and it's about a 16% volume difference. So as long as the system is is in hydrostatic equilibrium, so it's supported by the liquid column, then as it crystallizes, it's going to shrink. So my little artwork shrunk there. And their premise is that at the point where the solidification fronts or the capture fronts meet in the middle, so it's not technically the solidification front, but where plagioclase grains are now touching each other from the top and bottom, they concluded that that now gives it structural competency, and that further crystallization now will create a pressure gradient from the center to the edges. So as crystallization is happening, liquid will be drawn from the center to the edges because there's more solid at the edge, so there's more volume reduction. And that will result in this kind of geochemical profile. So this is the model that they're basing this on. Okay, so I have problems with this. So I would dispute that at the point where plagioclase is now making interconnected chains, it provides sufficient structural competency to resist further shrinkage of the sill as it solidifies. There may come a point where that happens when it's almost completely crystallized or something. But at that point, you're not going to produce pressure gradients because I don't think you'll have 100% permeability anymore. You'll have porosity. You won't create pressure gradients. If it's in hydrostatic equilibrium, the pressure is transmitted immediately everywhere. At the point where you can start isolating things and produce domains which might have distinct pressures, they're not communicating by definition. So I'm not sure about that model. So an alternative would be that a new magma the magma composition has changed. We have other studies which have shown evidence for this, usually based on geochemical trends that are not consistent with either normal differentiation or reverse differentiation. You have conflicting geochemical trends that require more than one magma type. There are olivine-rich magmas in the Karoo, or olivine-rich rocks in the Karoo. I mentioned earlier the Mount Aleph intrusion in the southeast part of the Eastern Cape has lots of olivine-rich rocks at the bottom. So it's not that ludicrous to suggest. So how about we just have a later pulse of magma that has olivine on the liquidus? Would that sort us out? We don't need a lot of olivine. So there are picritic magmas in the Karoo. This recent study by Lou Ashwell and colleagues shows the distribution of high titanium picritic rocks. So they're around, and their main geochemical discriminant tool that they invoke is the use of titanium. As we can see on this diagram, the high magnesium is not exactly correlated with high titanium, but it was the most compelling one they found. So what we would expect to see then is in the areas where we have higher, if the MgO content is correlated with increased olivine, it should also be correlated with higher titanium if it's an influx of a picritic magma. And we don't see anything like that. In fact, we see the opposite. We see they're nicely anti-correlated here. I've used a log scale here just to emphasize the variations. There's one area here where they seem to be positively correlated, but that's not a place where there's any olivine. And also, where these picritic lavas are found is not where we need them to explain our rocks. The Nchee complex, just for reference, it would just be off down about here, somewhere just to the southeast of our area. So how else could we do it? If we want to modify more, like have a more local modification by crustal interaction, is that a possible way to induce the appearance of olivine? So normal crustal contamination is unhelpful because it silicifies our magma, promotes orthopyroxene. However, if we were to contaminate it with carbonates, then theoretically, depending on the composition of our carbonate, how magnesian it was, we could drag it back into the olivine field, at least locally. And if we homogenize that assimilant enough, it might be a slightly wider effect. But in the rocks we're studying, we're not seeing big domains that are olivine rich anyway. Is there carbonate accessible to us? This is the preserved outcrop exposure of the Transvaal supergroup. So these include a thick dolomite unit, the Malmani dolomite that underlies the Bushveld, for example, up in the northeast. It's exposed to the north of where we are now. It's possible that there was material preserved that's underlying the Karoos, so it's not exposed and we don't see it. So it's not out of the question, but there's no evidence that it is there. Another possibility is the effect of water. And so this is a stylized version, so that magnitude of jump is not calibrated to real life. It's just to show the direction of movement. So from the dry phase diagram, if we hydrate this, sorry, it went the wrong way. A composition can go from crystallizing plagioclase to crystallizing olivine if it's hydrated. Alan has shown this kind of thing for decades. So do we have evidence of that sort of thing happening? We do have evidence for dehydration of xenoliths. This is on the bottom left here, this is a xenolith of mudstone from the country rocks. The host rocks are quartzites and mudstones, or sort of sandstones and mudstones. So this is about 1.5 meter xenolith. There is nice evidence for dehydration, which I'm not going to show you in any more detail here. Just trust me. I'm a doctor. So there are little centimeter scale needle-like amphiboles found above the xenolith, but not below it. And there's a little reaction rim around it. The xenolith itself doesn't grow any metamorphic minerals in it, even though it's sitting inside this dolerite sill. But so we do have evidence for sort of on the scale of maybe 10 centimeters dehydration, where we can see textural evidence. We don't see any olivines in those rocks, but theoretically, if this kind of process happened enough, and we do have nice wet sediments around. And I've included this piece of layering because it's a layered intrusion workshop. This is the only place in any of these sills that I've found layering. So it's sort of the scale of a meter. There's some lithological variation here. The orientation of those layers doesn't correspond either to a horizontal surface nor to the inclined sheet contact, which is a few tens of meters away. So I'm tentatively interpreting that as a torn off block that came from near the edge. But there's no layering near the edge that actually would support that it came from somewhere else. But so we've got quartz normative tholiites that are part of a calcalkaline trend. They're all crystallizing plagioclase early on, but not olivine. So we do know that there is some olivine around. And to me, the most likely explanation is probably kind of localized post-emplacement or syn-emplacement magma modification, rather than an emplacement of a second magma type, at least based on the evidence from these particular sills. So I believe that's my story. So it's possible that there might be better indicators to test for a second magma type other than magnesium versus titanium. There was not any real strong trace element diagnostic tool that the Ashwall et al. Paper, or from looking at their data set, anything else that really distinguished the basalts from the picrites to make it obvious. One of the questions I was interested in knowing opinion from this group is the absence of, say, plagioclase inclusions in the olivine compelling as evidence that the olivine must have crystallized from a magma that didn't have plagioclase in it? Will olivine nucleate on plagioclase laths? Because I don't see that very often. And I wasn't sure if that was a growth nucleation preference, that even if they're crystallizing together, we won't get that sort of ophidic type texture in olivines. So in order to interpret those olivines, do we get crystallization sequence information from that? So that's it. Thank you very much.
Thank you very much, Steve. So I guess we can either have questions from the audience to Steve, or replies from the audience to Steve's.
Thank you. On the problem of D-shape profiles, maybe some suggestion. As far as I remember, for the problem of zone complex, Alaskan type complex, Murray and Human proposed that there is a dynamic differentiation that olivine in a flow of magma accumulates in the central part of the flow due to the viscosity effects. So may it be applied to your case? What do you think?
So yeah, I mean, I think again, still you'd want enough grain size contrast to facilitate that. And what I'm seeing here doesn't.
So we are not in the price top.
Yeah.
Okay.
So those, yeah. The other feature in these rocks, by the way, near the top of the Colesberg sill in particular, which is the best exposed one and the sort of thickest, that's where the layering is too. There is this thing about, I think it's about 50 meters or so down, 60 meters down from the top. there's a big incompatible element enriched zone, which I didn't talk about now, which I have previously tentatively interpreted as kind of this, I mean, not as a sandwich horizon, but as a kind of the Jean Bedard style tearing off the roof. And then there's great textural heterogeneity in that zone as well. So going from very fine grain and very coarse grain, even in the same thin section, which to me fits with, anyway, with some kind of localized enrichment zone near the top, but not at the top. But not a third of the way down either. But anyway, there was hands. Sorry. Steve.
Yeah, I was just going to make a comment on that flow differentiation idea, which has been around for a really long time, but it's also been, it was debunked a very long time ago as well. If you just look into the physics, the lateral velocity you can get is so small that your cylinder will need to be, sort of 1,000 miles long before you get any sort of significant lateral displacement.
Okay.
It just doesn't work to scale. It can work in really, really narrow things, so that sort of meter thick size you get.
Okay. All right.
How the magmas started out in the very luminous.
They're not especially luminous. I mean, I've forgotten now what the aluminium content is. Yeah.
12%. So how does a basalt with 12% aluminum or 6% NGO start out up near a north?
I mean, they're all the Karoo things are always crystallizing plagioclase first. So I mean, they.
That bit I got.
Yeah.
Send your projection. Then you've got them projected way up towards the north line.
No, well, they've got to be in that top quadrant to crystallize plagioclase first.
Well, yeah, that's
yeah.
How have you put there?
Well, I mean, I've calculated those normative end members and plotted them.
So the normative anorthite of a rock with 12% aluminum is like 70% anorthite.
Yeah, well, in the field of anorthite and statite silica. So it's normalized to those three end members specifically. So that doesn't include it's not 70% anorthite in the whole.
I don't think that tells you much about phase relations.
All right.
Basically, you ignore dioxide.
Yeah,
Right.
Yes.
Yeah.
Why not just put the bulk in melts and see what you get?
Yeah. So I think, so I need a more sophisticated plotting for sure. Yeah.
But also these are evolved melt compositions, so I guess they've had an earlier history. And so you think they have not crystallized olivine or anything else before?
Well, we don't see it as a phenocryst, and we see all the other things as phenocryst. So that's, if I found olivine phenocryst, then that problem goes away. So.
Well, I mean, things like nickel or something would indicate whether you had some.
Yeah,
What you would expect high. I think it's not unusual to see plagioclase phenocrysts,
right,
even if you have had an early history, including olivine and essentially pyrite.
Right.
It wasn't important. I just wanted to say that in the Tropsburg area, deep drill holes have intersected below the Tropsburg intrusion, thick transfer dolomite. So
okay.
I think based on John's comment, maybe the problem of olivine is not such a problem of the whole.
Is maybe helpful you measure the water content of the olivine at PIR.
All right.
So I think, and then you can say, oh, it may be the addition of the water.
Right.
Yeah, and drive the crystallization of the olivine.
Okay.
Similarly, I don't know if the melt inclusions in the olivines.
Nope.
That would be interesting. So like unit in the bushveld, some of the issues.
Okay.
There's hydrous fluid and hydrous fluid melt inclusions in the olivines.
All right.
Just one comment, palisade still, thicker, 300 meters.
Yeah.
But it has the same disc shape,
Okay,
saucer shape, and the center is thicker than the edges,
okay,
but they're both S shaped.
okay,
Very similar profile.
all right,
Almost, you know, put one right on top of the other.
okay.
Yeah, to change track a little bit, really interesting. So I noticed on the cross section that you sketched in the learn work, each sill was fed by its own dike.
But
And
that part they don't know, of course.
so we see saucer-shaped sills like this in many sedimentary basins around the world, and there's a growing body of evidence that those sills are interconnected with each other, such that you don't need individual dikes for sills. So I was just wondering whether any of your data here or anything that you've seen lends support either way to whether these sills are fed by their own dike or whether there is some interconnection between that.
That was kind of part of the point of doing a study like this, because it's a much less thorough study than the Galern type study. The idea was if the interiors of the sills are actually fed by kind of backwash from the outer parts, then they should be more evolved in the middle, if anything. And we don't see that particularly. So yeah, that's completely wide open from the point of view of these models as to where the feeders are actually coming from. So yeah, I think in order to shed real light on this, we would have to be more systematic study done to try and link those up. So yeah, I don't think that's constrained by these kinds of data as it stands. So, and I don't think there's any existing model that would preclude that at all. There's places I know that Alex Kisters in Stellenbosch, who's doing structural analyses of these types of things further to the west, has found places where there's about 6 in one nest, kind of these sills. And we can see places where we can see them in outcrop cross-cutting each other. But so, and they've all got to be in place at about the same time. I mean, I think this has implications for how layered intrusions form and the kind of things we'll be talking about over the next few days, probably with like new pulses coming in under old pulses potentially. Here, these are it's one event. These are a couple 100-meter sills, so it's like a new pulse in a layered intrusion, but everything is definitely solid and they're cross-cutting each other, at least in some parts of the system. So why does it do that here? It's not inflating it and creating a layered intrusion. So yeah, but the possibility of then having some of these feeding other ones, presumably that it's all to do with small windows of timing then. When is it going to cross-cut it, which it seems to be mostly doing here, and other places where it's actually able to inflate existing ones or feed new ones. Yeah.
Okay. Thank you very much, Steve.
Sure.
Next is Mary Hollis.
Let's leave each other.